Okay, one thing that I feel like we're getting a lot of confusion about, and the reason there's a lot of confusion is because it's genuinely difficult, is, you know, okay, so I'm just going to review a bit of this, because, like, genuinely it is quite tricky, these types of questions, whether you're doing an ordered selection or an unordered selection, and it can make a big difference, in the solution. So let's say you have 6 balls are in a bag, and let's say they're labeled. You have ball A1, A2, B1, B2, C1, C2. Okay. And what I'm going to do is I'm going to remove 4 balls. From the bag without replacement. Okay, meaning I just take them out, I don't put them back. So let's look at two different problems here. So what is the probability? Oh, and I removed these balls randomly, right? So what's the probability that both of the A balls are removed? Okay. And as a second problem, I'm going to say, what is the probability that the first 2 balls that you remove are the A balls? So let's say we're removing these one at a time. And yeah, what's the probability that the first 2 removed are the A balls? Okay. So the reason I'm giving you 2 different problems here is I'm trying to give some feeling for like when you want to use ordered selections, when you want to view it as an ordered selection, when you want to view it as an unordered selection. And for some problems, you're forced to think of it as an ordered selection, and sometimes you're not. So is it clear what the questions are asking? So if I ask you this one, do you think you should think of this as an ordered selection or as an unordered selection? Yeah? How come? Yeah, exactly, yeah. So to just repeat that a bit louder, here I'm talking about the first ball and the second ball, right? Like the first 2 balls. So here the order matters, right? Meaning like the order you actually take the balls out. Like if I get the second ball is an A and the last one is an A, that shouldn't count, right? So it's the order matters, so it's an ordered selection. So if we're thinking of this as an ordered selection, how many choices are there? Well, to pick 4 balls in an ordered way, so we care about which one comes first, which one comes second, etc. The number of ways to choose 4 balls would be 6 choices for the first, 5 choices for the second, 4, and then 3. Okay. So now let's think about the numerator. How many choices are there for the first ball if I want to satisfy this condition? Yeah. Yeah, 2, right? Because it could be ball A1 or ball A2, right? And then for the second one, I've actually only got 1 because if I pick ball A1 first, it has to be A2 second, right? How many choices for this one? Yeah, 4, right? 4, 3. So yeah, that should be your answer, which is 1/15. Okay. Is it clear that this has to be, oh yeah, sorry. It is, yeah, that the number, like the denominator, for example, like that's the number of permutations of 4 elements from a 6 element set. So in some sense, I am using permutations to compute this bottom. I just didn't say it that way. For the top, I guess it's also permutations because you're taking a permutation of A1 and A2, and then a permutation of the rest of them, but you're only taking 2 elements. So yeah, this totally is a permutation thing. Yeah. Any other questions? Okay, now here's the thing about this other problem, so this first problem. If we're just asking for the probability that both of the A balls are selected, well, that doesn't really have anything to do with the order of the balls, right? It's just saying at some point you got A1 and at some point you got A2, right? Now I want to be sort of clear that, so here you have no choice, right? Meaning you have to think of this as an ordered selection. You can't really think of it any other way. Here actually you could do it both ways. It's just that doing it as an unordered selection will be easier. So you can think of this as an ordered selection or unordered. But we'll kind of see that this is going to be easier in this case. So let's think of it as an unordered selection. And when I say that you can think of it both ways will give the same answer. So it's not like you get different answers for both different ways, right? Okay. So I'm computing a probability. What should be the denominator if I'm thinking of it as an unordered selection? Yeah. Yep. Right, that's the number of ways to take an unordered selection of 4 items from 6 items. Right? So now for the numerator, I'm going to say, basically, I've got 2 choose 2 ways to pick the A balls. And then once I've chosen those, and this is kind of a silly thing to write because it's just 1. 2 choose 2 is 1, but it doesn't really matter. You can write it. And there's 4 choose 2 ways to pick the other 2 balls. Okay. which, oh, I don't think I computed this one, but this will be 6 over 15 or something, maybe. I think it's something like that. Okay. By the way, if you're skeptical about this, like this numerator, this example is small enough that we can just write them all out, right? So you can have, like your selection could be A1, A2, B1, B2. It can be A1, A2, B1, C1, A1, A2, B1, C2, A1, A2, B2, C1, A1, A2, B2, C2. Only one more, A1, A2, C1, C2, right? And since we're doing an unordered selection, if I choose the same set of things in a different order, we don't consider that as different. So we just have these 6 possibilities. So that's why this numerator is equal to 6, right? So the 6 comes from those 6, but yeah, you compute it like this. Okay, let's see how we can compute the same thing with it, thinking of it as an ordered selection. Okay, so if it's an ordered selection, we again have the same thing on the this 6 times 5 times 4 times 3 on the bottom, which, like as was mentioned before, is the same as P6, 4, right? Okay, so so I want to think of this as an ordered selection. I think of, like I've got 4 positions, and we want to say how many ways can I like choose positions for things, right? So my rule is I have to have both of the A's in here. So how many ways can I choose the position of A1? Well, there's 4 choices, you know. So this is where to insert A1. Once I've done that, I've got 3 choices for A2, right? And the way I'm going to think of this is, so suppose I put A1 here and A2 here. Now I'm going to start thinking of the positions left over. So how many ways can I choose what goes here? So it's going to be either B1, B2, C1, or C2, right? So I've got 4 choices for that spot, and then 3 choices here. Hopefully I got that right. Looks right. Which, if you compute this, you're going to get hopefully 2/5 again. So you get the same answer in 2 different ways. I don't know which one's easier. I kind of feel like, well, I kind of feel like this one's easier, but it's up to you which one you want to use, right? Okay. Any questions about that? Yeah, I just wanted to kind of go back to this stuff because, oh yeah, go ahead. Yeah, it just make sure to read the question carefully. If it asks for a certain format, then make sure to match that. But if it doesn't say anything specific, you can write it like this or as a decimal or whatever you want. So, yeah. It's a paper test. Yeah. Yeah. Okay, yeah. That won't be on ours, yeah. yeah, things have been shuffled around a bit, and we're doing the test maybe at a different time as before. So, yeah. Or yeah, I think so. Yeah. Okay. It's like this or something. Does it look like? Oh, lowercase a. Okay. Okay. Any other questions? Oh yeah. Oh, sorry. Oh, here. Yeah. Just come to class as normal tomorrow. Yeah. Uh-huh. Uh-huh. You should think of it like a numbered ball because it's kind of like you have red and white numbered balls because let's say you're lining up people, you can tell like not all women look the same, not all men look the same, right? So you can tell the difference between them if you swap them in the lineup. Yeah. Unless you've got like twins or something in there, then that make it more complicated. Any other questions? Okay. Let's go back to section 6.4. Which I know nobody really cares about because it's not on the quiz and it's not on the test, but you'll eventually have to do this, so. Okay, so let's say you have a survey of 100 UVic students about their major, like what degree they're doing, and food preferences. Showed the following. So we've got, for some reason, this sample only contained business majors and other. Okay. I don't want to write a million columns here, right? And they were asked, what do you prefer? Do you prefer caviar or pizza? So I guess most college students may prefer pizza. Business majors have a lot more money than the rest of us. So they prefer caviar, just slightly, I don't know. This isn't like an actual survey, so. So let's pick a random student, right, from this group. Pick a random student from those 100. And so let's say E is the event that that student is a business major. And F is the event that they prefer pizza. Right. And then the question is just, are the events E and F independent? Okay. actually, if you think about it, do you think that who thinks that they are independent? And who thinks they're not independent? And the rest of us are probably going to wait for the calculation to figure out what the answer is. There's a little bit of a hint here, though, that like, I mean, if I pick a random person and somebody tells me, oh, it's a business major, you should think, does that make me more or less, given this data, does that make me more or less, like, does that make me think that they're going to like caviar more or less than if I just don't know anything about them, right? If I pick a random student and I don't know anything about them, probably they're going to be like in this group more likely, and then they're more likely to like pizza. But if I know they're a business major, I know they're more likely to like caviar. So that should be giving you some indication these are not independent events. But to do it formally, we just have to compute the probabilities. So if I pick a random person from these 100, what's the probability that they're a business major? Well, you know, the number of business majors is 35, right? Out of 100. So it'll be like 0.35. Can anyone tell me what's the probability that they prefer pizza? If I pick a random student. It's something over 100. Yeah. Yeah. So, you know, pizza is going to be these two. You know, this row is pizza, right? And now let's say what's the probability that, like what's the probability of E intersect F? It's again something over 100. Any thoughts about that? Yeah, exactly. So 0.15, right? Because the intersection is just this entry, right? This is the probability this is the number of people who are business majors and prefer pizza. So we should check. So remember, these are independent if the probability of the intersection is equal to the product of these probabilities. What's the product of these two probabilities? Yeah, 245 or something, or was that right? Anyway, these are not the same. Right, so therefore, they're not independent. Because independent means, there's several different meanings of it, but one thing is that this product should equal this probability of the intersection. Oh, this should equal those two? Well, that kind of comes back to this equation that like the probability of E given F should just be, if two things are independent, then the way to think of that is that the probability of E happening, if I already know F happens, like F should not influence the probability. So basically, the probability, if I know F happens, the probability that E happens should be the same as if I didn't know anything at all, because they don't influence each other. If you kind of write out this formula and manipulate it, you see that it's the same as saying this product equals this. So that's kind of maybe a couple of extra steps there, but any other questions? Okay. So we've been talking about independence of two events. You can also think about multiple events. So a set of events is independent if for any events E1, E2, up to En from this set, the probability of E1 and E2 and up to En is equal to the product. So probability of E1 times probability of E2 times ... up to the probability of En. This is the terminology, and this is the way it's defined in the textbook. If I wanted to be pedantic as a mathematician, we would always say the word mutually here, but yeah, you don't need to think about that. Let's just, you can just say independent if you want. Let's do a quick example where you have three independent events. Just to sort of see how it works. So let's say Alice, Bob, and Chris are Math 151 students. And let's say that the probability that Alice misses class is 0.01. Alice shows up all the time, pretty much. Probability Bob misses class. Bob's a bit more unreliable, so 0.09. If any of you are called Bob, then I'm not, don't take it personally. Probability Chris misses class is 0.04. So here's the question. So assuming these events are independent, what is the probability that exactly one of them misses class? Not quite, because I'm saying exactly one. So if you had the complement that none of them miss, then you could have 2 or 3 missing class. Okay. So let's say that oh, yeah, so exactly one. Okay, so let's say A is the event that Alice misses. And similar B is for Bob. C is for Chris. Then what we want is to get like the probability that Alice misses and Bob doesn't and Chris doesn't, plus the probability that Alice doesn't, but Bob does, and Chris doesn't, plus the probability that Alice doesn't miss, Chris doesn't miss, or sorry, Bob doesn't miss, and Chris misses. Right, because this is what it would mean, yeah, for exactly one to miss class. Okay. You do have to be a bit careful when you're doing this because, so one important thing is that these events are all mutually, what do you call it? Mutually exclusive, exactly, yeah. So it can't be the case, like it's impossible for Alice to be the only one who misses, and at the same time, Bob to be the only one that misses, right? Because those two things can't happen at the same time. So when I want the probability of like this happening or this, since none of them can happen at the same time, I should just add up the probabilities. So now using independence, we know that, so the probability Alice misses is 0.01. The probability Bob doesn't miss is 0.91. And the probability Chris doesn't miss class is 0.96. So basically, because these things are independent, we can just break up the probabilities like this. So this isn't always true, but since A and B and C are all independent, the same thing holds for their complements, and you can always break up the probabilities like this. So this is by using independence. So this will be so the 0.96, right, comes from the complement of like a 0.04, right? And I've realized the question I wrote here is not the same as I wrote in my notes, so I don't know the answer to this. But so I'm guessing 0.1 something, or well, okay. Anyways, it's yeah, it's something. Any questions about that? So basically, the important thing is if you're ever told that things are independent, that means you can, if you're computing some intersection, you can just break it up into multiplying the different things. If it's not independent, you can't do that. Okay. So let's do a little bit more practice with another example, this time using a Venn diagram. So let's say you're in this situation where you've got two events, E and F, where the Venn diagram has these probabilities. Let's say it's 0.3, 0.1 here, 0.4, and 0.2. You can check this adds up to 1. let's say part A is what is the probability of E conditioned on F, or E given F. Okay. So this one, if you remember the formula for this will be very quick, because you can just say, okay, it's the probability of E intersect F divided by probability of F. So this is just a formula you need to memorize. Does anyone see what the numerator it should be? Oh, sorry. Probability of E intersect F here. Yeah, I hear some mumbling, 0.1, right? Probability of F, you have to be careful, right? Because it's not 0.4, right? F is this whole circle, so you want to take 0.1 plus 0.4. So in total, you get 1/5. Or, in other words, 0.2. So here's another question. Are E and F independent? So, any thoughts about this? So if yes, why? And if no, then why? So I think at this point, once I've computed this, the easiest way to answer this question is I'm going to compute probability of E, which is 0.4, which is not the same as the probability of E given F, which is 0.2. So therefore, no, they're not independent. Yep. Yep. Yep, that'll totally work. So kind of second way of doing it, if I take, so we already know that this is 0.1, and if I take probability of E times probability of F, that's 0.4 times 0.5, which is 0.2. And you can also say, these are not the same. Okay. So totally valid to do it that way. That means, so that's something which is tricky with the terminology. So having no intersection here means that they're mutually exclusive. But mutually exclusive and independent aren't the same thing. Yeah. How about a variation of this problem, which is maybe a little trickier? So let's say my Venn diagram now looks like this. So here I've got probability 0.3 minus x for some x. Here I've got 0.1 plus x. Here I've got 0.4, and outside I've got 0.2. So my question is now, for which value of x are E and F independent? If this was asking about mutually exclusive, then you'd want x to be negative 0.1, so they have nothing in common. But we'll see independent is a slightly different thing. Okay. So what we want here, we want to find the x so that probability of E is equal to probability of E given F, right? Probability of E is just the sum of these two values, which is still 0.4 because the x's cancel. So we want right, because this came from 0.3 minus x plus 0.1 plus x, which is 0.4. So if I'm computing this at conditional probability, what's my, let's say, what's the numerator? The top of the fraction. Yeah. Yep. So, and in this case, the probability, so this should be, yeah, like you said, probability of E intersect F. Right? And in this case, that's 0.1 plus x, right? And now the denominator is going to be the probability of F, which is, if I add these up, it's 0.5 plus x. So now we just solve for x. In this equation, right? So I bring this over, so I've got 0.4 times 0.5 plus x equals 0.1 plus x. Right, so the 0.4 is over here. I've just multiplied that over. Right, so you got, you kind of multiply these things out. That's 0.2 plus 0.4x equals 0.1 plus x. If I kind of get the x's all together and the other stuff all together, I've got this. So x is equal to 1 over 6, because 0.1, you know, over 0.6, which is 1 over 6. Okay, and if you plug in that value for x and you compute things, you can see, oh, yes, they are independent. Any questions about that? Yeah. Yeah, so this is, I've got this fraction equals 0.4. And I just move this over, right? And I've got this equation. And then I multiply the 0.4 inside. 0.4 times 0.5 is half of 0.4, so it's 0.2. 0.4 x and then solve. Yeah. Yeah. if x is equal to 1 over 6, then they are independent.